Good. Okay. Dr. Jim Bell is a planetary scientist, educator, author, and public speaker, and was the president of the Planetary Society from 2008 to 2020. He works at ASU and is heavily involved in NASA solar system exploration missions like the rover Spirit, Opportunity, and Curiosity. Welcome, Dr. Bell. You have the floor.
Cool. Well, thank you so much for inviting me. I don't actually have a formal presentation. What my hope was that I was going to, I understand, and correct me, Nicole, or fill me in, but my understanding is that the students are working on a variety of projects. Is it multiple teams?
We have 15 teams.
Right, right. And so I'm sure they span a wide range of technology, engineering, science, exploration, all that kind of cool stuff.
Yes.
Um, and I was just going to say a few things about my background and experience in the Mars world, and then kind of open the floor and hopefully help answer some questions, provide some feedback, um, uh, help provide pointers to resources if people are stuck. Um, if, Sounding board for, is this a crazy idea? That kind of thing. I enjoy doing that kind of stuff. And I thought that would be better than just me sitting there flipping through slides that are probably everybody in this particular group has already seen already, because I'm sure the room is full of Martians here, like me. Um, so that sounds okay? All right,
Sounds
great,
great.
great. And right, so as Nicole said, I'm a professor at Arizona State. I've been here about 15 years in the School of Earth and Space Exploration, where we do a lot of different NASA-related robotics work. Um, as Nicole said, I've been involved in a number of NASA missions. My career, I got my start with the Mars Pathfinder, which probably landed before most people on this call were born, um, in 1997. Um, and that was exciting because it had been 20 years since the Vikings landed on Mars in the mid 70s. And the Vikings lasted about 4 years, the longest lasting of them. And then there was this long gap where there was just really nothing, very little going on at Mars. I was going to undergraduate and graduate school during that long gap, and ended up spending a lot of time using telescopes to look at Mars and the moon and other planetary objects, because there weren't all these missions. But then, right when I got out of graduate school and became a postdoc and then an early career professor, that's when all those missions started coming back, like Mars Pathfinder and other of these so-called better, faster, cheaper, smaller missions that NASA started doing. Mars Global Surveyor, Mars Odyssey, Mars Reconnaissance Orbiter, Lunar Reconnaissance Orbiter, and then a whole series of missions under the Discovery program, to do small missions like the Near Earth Asteroid Rendezvous. I got involved in that one as well. And so I've got a lot of experience working on these mission teams with working with engineers and operations specialists and scientists. And I'm ultimately, at the end of the day, a scientist. I'm the end user for all the cool tools and toys that my engineering friends and colleagues build and launch and land. I'm a geologist, mostly a little study mineralogy and surface geology. Uh, but I'm also kind of an astronomer because I did have to learn how to use telescopes and spectrometers and things like that earlier in my career, and still use some of those kinds of tools in payloads on NASA Mars rovers and Mars orbiters and lunar orbiters and asteroid orbiters, etc. So I've spent a lot of time living vicariously on Mars through these robot avatars. Um, you, you may or may not know that we have had active missions on the surface of Mars returning new images and other data every day since January 4th, 2004, when the Spirit rover landed. It's been continuous for more than 20 years now. And so it's just one of the most special parts of my day. Every day for the past 20 years has been coming in and seeing the latest pictures, coming back from Mars, and scratching my head like everybody else and wondering what's going on and trying to put the pieces together. We run the cameras on the Perseverance rover, the Mastcam Z cameras here at ASU, a staff of 15 or 20 people, and uh, students and staff, about 15 to 20 people, who are operating those cameras for NASA and JPL every day, taking the data, writing the sequences with our friends from Mail and Space Sciences in San Diego, and making the mosaics, panoramas, all the cool stuff, making the movies. If you've seen movies of the Ingenuity helicopter flying on Mars, that's the team here at ASU. We put those together. So that's kind of my background. I work a lot with students and student groups. I'm the advisor for our SEDS chapter here, um, at ASU. For a while, we had a Planetary Society chapter here at ASU. We've hosted the Mars Society conference here at ASU in previous years, which is a lot of fun. So I'm often working with and answering questions from student groups, doing capstones or other projects that are related to Mars or the moon. A lot of interest in lunar exploration these days as well. Um, so I think, Nicole, that's kind of a high level background and kind of the broad brush envelope of my experience, umbrella of my experience and interests. I'm interested in lots of things across the solar system, um, and involved in other missions to asteroids and the moon, for example. But would be delighted to hear more about what you all are working on, and especially places where you're stuck and could use some advice, guidance, resources, questions that you might have that are scientific in nature, questions that you might have that are even about policy or the future, um, that kind of thing. So, don't know how you want to do the Q&A.
We'll have a combination. A couple of questions are in the chat. We'll start there. One of the questions is there any way to speed up the transmission time of signals from Earth to Mars? That's a great question.
It's a great question. Sadly, the answer is no. It's not my fault. Blame Albert Einstein. Stupid speed of light. Um, no, we use radio now, and there are uh, plans and tests have been conducted in space for using optical, uh, laser optical transmission instead of radio, but it still travels at the same speed. You can have higher bandwidth. You get more information over laser optical than you can over traditional radio, but unfortunately, it still travels at the same speed.
And I have a question of my own about that very thing. Will quantum computing help with that at all?
It can't help the speed, but one could imagine it could help with data quantity or data quality, by encoding the data in ways that quantum communications folks are learning to encode data and messages. Probably will also be important eventually in the distant future when you want secure transmissions between Earth and the Moon or Earth and Mars, for financial transactions or defense or whatever. Um, but I think it's probably a ways off.
Okay, I have five follow-ups, but I'll skip them
Okay,
because the students want to ask questions.
all right.
Jad says, to what extent have the discovered clay minerals influenced models of the potential presence of liquid water in Mars past?
Yeah, that's a great question. Certainly, we've known for a long, long time that there is water on Mars and as ice, because even early 19th century or late 19th century telescope observers could see the polar caps coming and going. And in the as early as the the 1920s, 1930s, the first spectroscopic evidence started coming in that that's water ice. So we know there's water ice there. And in the 50s, telescopes again started telling us that there's a little bit of water vapor in the atmosphere. So that's pretty cool. But these are small quantities that have been known to be there for a long time. But it wasn't until really until the spacecraft got there and started looking at the surface in great detail that clay minerals started getting discovered. And the cool thing about clay minerals, if anybody does pottery out there, you know this, right? They're loaded with water, and this is why you have to bake them out. And it's not just water that's evaporated onto the surface; it's the structure of the mineral is these sheets of silicon and oxygen with water between the sheets, right? And so it's a great way to capture and sequester, hold on to a bunch of water from the past. So, when we see these clay minerals, we're looking at that ancient water that used to be flowing across the surface of Mars. So it's one of the pieces of evidence that Mars did have a watery past, that liquid water flowed on the surface and in the subsurface of Mars long ago. Of course, it can't now, uh, because the temperature and pressure is so low, it would just boil off into the atmosphere. But long ago, the climate of the planet was dramatically different. Most planetary scientists who study Mars don't think that it was ever really like the Earth. But we can think of it as Earth-like in that it was warmer, it was wetter, probably never tropical, probably never even as nice as Antarctica, right? And Antarctica is one of the harshest places on the Earth. And it's not clear that Mars was even that warm and wet. But we don't know for sure. And part of what we're trying to put together by studying different places on the planet, by detecting different kinds of minerals and geologic evidence for liquid water on the surface is what was it really like? How thick was the atmosphere? How warm did it really get? How much water really flowed across the surface? How much is still in the subsurface as aquifers or ice? Uh, these are all questions that we don't know the answer to. So if you read some paper or article or blog that somebody says they know the answer, don't believe it. We don't know the answer. That's why we're still exploring and still need to take measurements. And probably ultimately it's going to take, just like on our own planet, probably going to take field geologists crawling all over that planet in great detail at some future date and time to really figure it out.
Wonderful. Noir, you are next.
Uh, I'm Nawar Karam from Syria and I'm from Saraya Smart School team. I'm really honored to be a part of this lecture. However, I have a question. My question is, how has our understanding of Martian geology evolved due to spectral analysis conducted by rovers such as Opportunity or Spirit?
Yeah, thanks, Noir. It's a great question. Um, it it's been super important, just like on the Earth, to have something that we call ground truth, right? On the Earth, you have satellites, they do remote sensing, or airplanes, they do pictures or spectroscopy. The satellites are doing spectroscopy, and typically they're looking at big areas the size of a tennis court or a football field or something like that, right? Maybe a little bit smaller in some places. And they say, okay, here's where there's this oxidized iron mineral, and here's where there might be some copper, and here's where there's some, rich deposits of sulfur or whatever, right? And you can see those things from up above. Sometimes, though, it's a you don't really know for certain. It's a weak signal. You maybe have to do a model to try to fit the data, and you're not quite sure. And we have the luxury on our own planet. Okay, let's just go there. Let's just go. Get in a helicopter, get in a Jeep, whatever, go there, scoop some of that stuff out of the ground, analyze it right there, or take it back to the lab and say, yes, this stuff is there. This is the ground truth. We understand this, and we believe what the satellite is telling us because we trust it We verified it in the laboratory, right? So on Mars or the moon or other places where we have satellites taking these global data sets, we don't have that luxury. We can't go and we all want to go, right? But we can't go yet. Go scoop up some of the stuff, bring it back to the lab and say, okay, now we can trust what the satellites are telling us. So the best we can do is send a robot to a few places, and we've only landed in 10 different places on Mars, right? It's a big planet, right? But at these 10 places, we can study the surface in detail with cameras and spectrometers and measure the elemental chemistry and the kinds of minerals that are there. In some cases, even look at some of the isotopes of the atmosphere or the surface minerals and get that ground truth. It's not as good as if we could do it on the lab here on the Earth because the technology is just so much better. I mean, the laboratories, you've seen laboratories in college, universities, whatever, big rooms full of heavy equipment, spectrometers and mass spectrometers and isotope measurement instruments and other kinds of things, right? We can't send all that stuff to Mars or the moon or other places yet, right? The rovers are good, but they're nothing like as good as the laboratories. But still, it's better than nothing. So we get some ground truth and we say, okay, now we can now trust that what the orbiter, what the satellite is telling us here, we believe it. And therefore, what it's telling us about other places where we don't have the rover, we can believe that too. So that's really the value, one of the pieces of value of having rovers and landers on the surface is to get us that ground truth. So now we can believe the whole global story from the orbiters above.
Great answer to that great question. Laksh, you are next.
Okay, yeah. My name is Laksh. I'm from India, Team Solis. My question mainly has like two parts. One of them being from all the like rovers and the orbiters sent to Mars by NASA or ESA, what is the most important geological discovery that you've made that has gone unexplained till now?
That has gone unexplained?
Yeah, like you don't have the answer to that why that happens.
Well, technically all of it. I mean, technically, we don't have definitive answers on almost anything, right? You can say, okay, water flowed down this slope, but how much, when, where did it come from? Did it rain or did it burst out from underground? I mean, um, I, I think we all just need to have a little humility that there's very uncertain exactly how uh, uh, Mars evolved or what it was really like long ago. But that's kind of the biggest question, you know, what it seems like it was more Earth-like long ago. How Earth-like was it? How long was it like that? And are there places that were much more Earth-like than other places? Are there places that preserved that evidence of Earth-like conditions better than other places? Are there places where some of that evidence might indicate that life existed there or still does exist in the subsurface? Right? These are big questions that are driving all of this, and we have no answer, no definitive answer to any of those questions, right? So
Yeah.
what we're doing as scientists is the best we can, which is pose a hypothesis, multiple hypotheses, right? Mars was Mars had oceans that were just like the Earth's oceans long ago. That's not a statement, that's a hypothesis. I pose that as a hypothesis and then I want to go test it. And so far, there's been a lot of tests of that, and the evidence is no, probably not oceans like the Earth had. Well, Mars had flowing liquid water in lakes and streams and maybe small seas. Well, there's another hypothesis, and there's better evidence that supports at least lakes and flowing rivers across the surface, but we don't know how long they lasted. Um, Mars has subsurface liquid water aquifers just like on the Earth. That's a hypothesis based on some evidence from orbit. You can see places where it looks like these valleys just appear out of nowhere from the underground. We see places like that on the Earth where there's a landslide or earthquake, and it'll disrupt the cover over an aquifer, an underground body of water, and the water comes splashing out and creates a big channel that seems to come out of nowhere. So the hypothesis is the same thing is happening, has happened on Mars. And so, okay, we can go test that hypothesis from orbit, or in the case of, Mars Pathfinder landed in a place where one of those floods occurred. And so there was evidence seen on the ground that, the rocks had been stacked by this big flood and all that. So there's no simple answer. It's a great question, but there's no simple answer, because the whole thing, everything we do is, covered in this veil of uncertainty. And the best we can do is pick up the veil a little bit here and there by asking questions that we can test with observations from orbit, observations from the surface, or laboratory studies or computer models. So maybe not a satisfying answer, Laksh, but hopefully that makes sense.
Yeah, thank you.
I would like to move on for sake of time and respect to Dr. Bell to Sham, your question, please. And Dr. Bell, please let me know what your cutoff time is, because there is a lot of hands
Okay.
raised.
Okay. Well, it turns out, let me just double check. I can go till 3 o'clock Pacific, if
Okay.
the students want to as well. So.
Okay. Thank you, Dr. Bell. Sham, go ahead.
Hi everyone, I'm Sham Basad from Syria in Sarai Smart School team. And my question is, how can we address the challenges posed by the chemical interactions of Martian soil with scientific instruments in future missions?
Yeah, great question. And this is going to be important for, of course, when people go, right? And the equipment that people bring and the space suits and all that kind of stuff that interact, boots that interact with the surface, all that kind of stuff. So there's a couple of ways that I know that question is being addressed. One is by studying material that's Earth soil that comes close to, or is created to be close to, what we think Mars soil is like. And it's called analog soil. And so we know that there's this much iron and magnesium and silicon and oxygen. We don't know everything about what the Mars soil is like. So that's partly why we want to bring samples back before we send people. There's lots of aspects of it that we don't understand. And of course, there's nowhere on Earth that is really like Mars, with that low atmospheric pressure, very low temperatures, and all that ultraviolet radiation from the sun coming down to the surface, because there's no ozone layer to protect the surface. So we can't get a perfect analog. But yet, people trying to figure out exactly the answer to that question by studying Earth soil that's simulating Mars soil. The other way is there's direct measurements from the landers and rovers of the chemistry, of the kinds of minerals that are there, of the things like the pH, and some of the technical properties of, how do wheels interact with the soil? How does a scoop interact with the soil? What happens if you add ice, like from the Phoenix lander mission, ice and soil mixed together? So the rovers and the landers are also helping to answer that question.
Thank you. Layla, you are next.
Hello,
Hello.
I'm Nora from the Sarai Smart School team from Syria. Well, thank you for your time, but I do have a question. Given the detection of methane in Mars' atmosphere, to what extent can this be considered an indicator of biological activity?
Great question. You're not going to like my answer, but I'll tell you what it is anyway. That detection is very controversial. It is not certain that methane has been detected in the Martian atmosphere. Just because somebody writes a research paper about it and it appears in a scientific journal doesn't mean it's correct. It's one explanation for the data. If there is methane there, and maybe there's a little bit, really tiny amount, um, and some telescope observations even back decades ago imply that there might be a tiny amount. It doesn't have to be biologic. There's non-biologic ways to make methane. It happens on the Earth as well. Some minerals, the way they interact with water, um, and the way that some of the minerals have carbon in their structures and water has hydrogen. Methane is CH4. There can be reactions between those kinds of minerals and water that create methane. Entirely no biology involved, just geology. And it can produce small amounts of methane. On our planet, most of the methane that we can measure in the atmosphere today is coming from biology, cows and other, sources of methane. But it doesn't mean that that's the case on Mars. It's true that there is biology at the, microscopic microorganism level that can also produce methane in small amounts. So if you measure a small amount of methane, it's possible it could be due to biology, but that's not the uniquely only answer. So what scientists do is work really hard to consider all the possible explanations for what's being measured, including one explanation is the measurement is in error. And because it's a very, very small amount, it's a very sensitive measurement. There's lots of noise in the data, and people work really hard to pull the measurement out of the noise and put their ideas out there. But not everybody is convinced that it's methane. And even if it were, it doesn't have to be biologic. So we need to keep making better measurements. We need to also keep our eyes open for the fact that there are non-biologic pathways to make methane. And at the end of the day, we'll have to use this concept called Occam's razor, where if you have many different possible explanations for something, nature generally picks the simplest. So what's the simplest explanation? If we know that some of those minerals that can produce methane on Earth are on Mars, we know there is or was water on Mars, so maybe that's the simplest explanation. But the jury's still out. Great question.
I would just say that, just to interject, the simple explanation could also be that all of the minerals to make life exist on Mars. So I just
Certainly all the elements do. Absolutely. Absolutely.
so next question. Thank you, Dr. Bell. I'm a big proponent for life on Mars. So
Me too. Me too. But I'm also a big proponent of actual evidence. So
yes, agree,
yes,
agree.
yes.
Yes, the science. Got to do the scientific method. Dana, did you already ask your question?
My name is Dana. I'm from Syria, from Sarai Smart Schools. And my question is, what's your opinion in using ISRU to predict advanced polymers as high density on Mars?
Great question. I got to say, all of your English is outstanding. Everybody who's asked questions so far. So yeah, there's a lot of people thinking about ISRU as in many different ways, both for life support, construction, habitats, resources, other kinds of resource extraction, heavy metals, helium-3, energy. There's all kinds of great concepts floating around out there, and some of those concepts are going to get started to be tested for real in space and on the moon pretty soon. We had one test on Mars of creating oxygen out of the CO2 atmosphere with the MOXIE instrument on the Perseverance rover, and it was just a small tech demo, basically using 19th century chemistry, but packaged in a 21st century way on an incredible robot that demonstrated that you can extract that oxygen resource from the CO2 atmosphere. So, it's going to be important on Mars and on the moon to try to figure out, what can we extract. And water is going to be the most important extractable resource for a while, for partly the reasons that you already know about. Of course, we can drink the water, we can separate the oxygen from the water to breathe, we can make rocket fuel out of the oxygen and hydrogen. We can use ice to protect us from radiation, ice and water to protect us from radiation on Mars. Many different possible uses. So it's an exciting area that I think it's just going to be growing bigger and bigger in the decades ahead.
Thank you so much. Karun, you are next.
Hi, sir. I just had a simple question. Do you think in 10 years, technology will have evolved enough to make transmissions between Earth and Mars instantaneous? And if you think so, is that realistic enough for us to use in our mission plan?
Unfortunately, I don't think so. But it's because I'm a scientist, I follow the evidence and understand the laws of physics. And nobody's demonstrated that that concept. Not only has nobody demonstrated that concept can work, but there's no widely accepted peer-reviewed theory that explains how that could work. So it all depends on how you want your mission to be, how you want to do it strategically. You could invent things. You could assume some technology or capability comes along that all of a sudden changes. It would be a game changer, like that would be a total game changer. But then you just have to acknowledge that your project is science fiction, not science.
Great question. Magd, you are next. Magid, sorry if I mispronounced that.
Good evening. I am Majd Al-Dali from Syria, from Saraya Smart School team. Thank you for this beautiful meeting. And my question is, how do atmospheric conditions and dust variability affect the effectiveness of high-resolution imaging for exploration rovers?
That's a great question. And it does, especially the dust. The dust can have big effects on our ability to take high resolution pictures, especially if we're looking like out at the horizon, like in the Jezero crater where the Perseverance rover is. We often look at the rim of the crater, like the picture behind me is from Jezero crater. And if it's clear, there's no big dust storms, no dust devils zipping around, then we get beautiful high resolution pictures. But as soon as the dust comes in, and it comes in with season, sometimes in the summertime in the southern hemisphere, it's more dusty. It's very repeatable from year to year on Mars. When it's more dusty, we won't see these features. We might not even see the rim of the crater. It gets dusty enough. And this was a big problem for the Spirit and Opportunity rovers in the 2000s and 2010s, because those rovers were solar powered. And so the dust would settle onto the solar panel and drop our power. And it's what eventually killed both rovers. Too much dust storms on those solar panels, and kills your power. You can't recharge the batteries. You can't run the heaters overnight, and you die. But with the Curiosity and Perseverance rovers, they're not solar powered. They're nuclear powered. So we don't have that problem with dust killing the rovers, but we do have the problem of it blocking our view when it's very dusty. We just can't see very far away. We can always see close. It never gets dusty like it does in the Sahara Desert in a big dust storm or a sandstorm. Or some of you may have seen the movie The Martian. Big sandstorm in the beginning. That's fiction. It never gets like that on Mars. The air is too thin. It's like being at 80,000 feet in the Earth's atmosphere. It's very, very, very thin atmosphere. And so if you were in a big dust storm on Mars, yes, it would block the light, but you would hardly feel the breeze. It would be like somebody blowing feathers, Like you take your pillow of feathers apart and put them in front of the fan and blow them across yourself. Not much, not much pressure, not much force. Enough to move a sand grain around and a dust grain, which is like the size of smoke, but not much force to it. So yes, dust especially affects our high resolution images.
Thank you. Jad, you are next.
Okay, good afternoon, Dr. Bill, and thanks for the great answers for the questions. I'm really having a question that says, how do cosmic radiations levels impact the potential of for sustaining life in extraterrestrial environments? And can we develop effective shielding technologies?
Yes, yes, great question. The answer is it depends. Mostly it depends on what the sun is doing. And you probably all know the sun goes through a cycle of 11 years of high activity and then low activity, and we're very close to the high activity of the sun right now. And when the sun is very active, there's more high energy radiation coming off the sun. And we've actually measured this on Mars with an instrument on the Curiosity rover for more than a whole solar cycle now. And so we know how much radiation comes down to the surface of Mars, and it's much more than hits the surface of the Earth, because the Earth's surface is protected partly by our atmosphere, which is much thicker than Mars, but mostly by our magnetic field, which is much, much stronger than the magnetic field of Mars. It diverts a bunch of that high energy radiation. It's what helps make life, complex life like ours, possible on the Earth, is our magnetic field. So on Mars, the astronauts and future settlers, they're going to have to deal with radiation as a serious health risk. It's many, 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 many X-rays over the course of your lifetime is the dosage. And so they're going to have to do shielding. They're going to have to be protected from that. One way is to live underground, tunnel yourself underground, build underground structures. Another way is to build structures that you cover yourself with soil or heavy metal or water or some other shielding thing. It's going to be important for people not only living on Mars and the moon, by the way, but people traveling back and forth there. The spacecraft are going to have to not only just use their metal skin as protection, but probably more than that, maybe heavy metals, maybe water as shielding. So when one of these storms that occasionally erupts from the sun that spreads high energy radiation into space, intersects that spacecraft, it doesn't kill everybody. There will be risk associated with that. So shielding, many of my engineering colleagues and friends are thinking very seriously about shielding for future habitats on the moon and Mars and other deep space destinations.
Thank you. Mohammed S., you are up.
Thanks a lot, Mrs. Nicole, and thanks a lot, Dr. Bell, about this important Q&A, important answers. And I have a very important question, please, if you don't have any problem. Doctor, please, what are, or there are a lot of movement mechanisms, especially those that were in previous rovers. So from your experience or experiments, Doctor, on what the principles that I can dependent on it to build an excellent movement mechanisms. There are a lot of important principles, as we can see, dependent on the weight of the rover, the control, fail and testing in control, balancing of rover, dropping down. There are a lot of important points, but what are the best points on your opinion, Doctor? And thanks a lot.
Sure. No, it's a great question. I'm not an engineer, but I work with many engineers and I see what they go through. And I can tell you one very important thing is test, 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 test. If you can get your system, your motors, your other mechanical, the mechanisms, gears, whatever the system is, if you can get them into a vacuum chamber if you can get them into Mars-like conditions, if you can bombard them with radiation, if you can blow dust and sand across them at low pressure, if you can get them down to cryogenic temperatures and cycle them up to just above freezing, and then, you know, 10 degrees C to minus 120 degrees C, 1,000 times, these are the kinds of tests that we do. This is why all these rovers and landers and orbiters, this is why they all work, because they've been taken through these extreme environmental conditions by testing on the Earth over a much more extreme range than they'll actually experience in space. When we sent the rovers to Mars, they were built for that environment. They are like wild animals in their native habitat, right? But Mars to them is like, oh, this is a playground, because on the Earth, we took them through much more colder temperatures and much hotter temperatures and much lower pressure and much higher pressure. The only thing we didn't do was get them dirty. We didn't blow sand and dust on them because, we knew that was going to be very harsh. But we did everything else that could be done to try to test for the conditions that you want to operate in. The thing they say at JPL at NASA is test as you fly. So, there's many different kinds of systems. I don't know exactly what you're building, but even if you can't test them in a vacuum chamber, if you can run a thermal model on a computer or a radiation model for electronics, or even modeling, if that's the only testing you can do, that's super important. In reality, the engineers from all these different space agencies, they do that modeling, and then they do the actual physical testing as well.
Wonderful. Lax, you are next.
Yeah, so I had another question. So this is more of a hypothetical question. If you could go find out everything you could about one particular factor of Mars, factor being would you go into the atmosphere, the poles, the Tharsis region? So what one particular thing would you go and exponentially into?
You guys like asking these impossible to answer questions. I love it. Gosh, I mean, look, I would love to go. I'm probably too old, but I would love to go, and I want to come back, by the way, because although I love studying Mars, it's not my favorite planet. Earth is my favorite planet. Hopefully yours too. But I think if I could, gosh, I don't even know where to start. Let me just pick one. I'll pick one, okay? I would like to be able to understand as you go down underground, how warm does it get? How much warmer does it get like every meter you go down? And is there liquid water down there? For sure. We don't know. We don't know
Thank
either
you.
of those things. We don't know either of those things. But if the answer is anything like it gets as warm as it does on the Earth as you go down meters to kilometers, and there is liquid water underground on the Earth, then we know that there is a vibrant biosphere underground. There's almost as much life underground as there is on the surface of the Earth. And if we find those kinds of environments in the subsurface of Mars, then that might be where we need to go to look for life.
Thank
That
you.
was awesome. And that was that Jad, or are you next?
Okay, thanks, Miss Nicole. I have another question, and that's my final one. Dr. Bell, do you think the development of autonomous robots can enhance scientific research efficiency compared to current models?
Yes and no. In many ways, the robots that are there now are very autonomous. They make a lot of decisions on their own based on information that we provide. And so, that's just a pragmatic, because they're so far away. We can't joystick them, right? They have to be able to travel safely long distances without human intervention. But up until now, even with the autonomy that they have, the robots they're not using AI. They're not intelligent in any way. They're not even as intelligent as an ant. You know, they're not making decisions. Even though it's robotics, it's people, human exploration. They're guided by people. Hundreds of people on the earth are guiding each of these robots across the surface, helping make decisions about what it should do and when and all that, giving commands, all that. So I can imagine a time when the robotics are much more autonomous, much more driven by highly trained AI systems that are trained by people to recognize certain patterns, to take certain measurements, to follow certain clues that a geologist or an engineer would follow to answer certain questions. I think that's going to be a natural extension of exploration, but probably they'll, in my opinion, never truly be able to replace people because a lot of the way that discoveries are made involves experience, intuition, feeling. You know, I think I should head left and right. I think I should pick this rock up instead of that one based on the decades of experience that I have out in the field or whatever, right? Things that you can't code, you can't program even into an AI. Very difficult. Now, it's one thing if I want to say, I want to send an automated robot to go count the number of rocks on that hill behind me. Absolutely, you can do that. You can do that kind of basic reconnaissance. You could do that all over the solar system. You don't truly need people. Give it a set of commands, a target, a goal, some simple quantitative equation that it can follow. Go for it. But to go and say, why are the rocks on this hill? Why are they in this distribution? And what happened here over geologic time? So far, there's only one AI, not AI, but in the intelligence in the human brain that is sophisticated enough to be able to do that and answer those kinds of questions. So I think it's a mix, right?
Wonderfully. Great explanation. Amir, you're next.
Hello everyone, my name is Amir Abu Fadl and I'm from Syria and working in Sarai Smart School team. And I'm really thankful for this amazing meeting. So my question is, what are the procedures being taken to return samples taken from Mars to Earth? Do you really think this is a necessary step before we begin a manned mission?
Great question. Complicated question. We've been trying to get a Mars sample return mission in NASA for 40 years. And it always seems to be 10 years away. And up until recently, it was much closer than it's ever been, and now maybe it's 10 years away again. It's very complicated. It's very expensive. But I also think it's necessary to the second part of your question. Yes, I do think it's important and critical to bring samples back. Well-chosen samples, not random samples, but well-chosen samples for a variety of reasons. Purely scientific reasons, because then we understand the details of the chemistry and the mineralogy and the isotopes and all that. Is how much methane is there and all these kind of science questions you can imagine. But maybe just as importantly is for the health and safety and planning for the people who go there in the decades ahead. You know, that we were talking about Mars dust earlier, and we know that there's something in the dust is very highly oxidizing. We don't know exactly what it is, but whatever it is going to have a pretty serious effect on spacesuits and seals and rubber tires or boots. And people's lungs, because when you go into the airlock and get into your habitat, some of that dust is coming into the airlock with you. There's nothing you can do about it. It's like smoke, right? One of the things that I've demonstrated to students is you take a bag of flour, like that you would make bread with, and you open the bag and just throw it all around the room, right? Please don't do this at home. But if you did this, you would see that tiny, tiny stuff, the very finest part of the flour, stays in the air a long time. and it gets in the corners, and it gets, on the floor, the cracks of the bricks on the wall. You will never ever get it out of everything. It will always be there. And the Mars dust is just like that stuff. And and so people are going to breathe it. And coal miners who work in coal mines have major health problems because they breathe the dust of the coal, right? It's called black lung disease. And so on Mars, there's going to be red lung disease from the very fine dust. These are health hazards. And can we grow plants in that material? Nobody knows. If you add fertilizer, will it accept the fertilizer and not break it down and so you can grow plant? Nobody knows, right? There's so many reasons to want to bring some of that stuff back and study it in detail and understand what are the implications for not just the science, which is of course great, but the health of the people and the ability for them to use it in their agriculture, in habitats, life support, etc. So um, there, the process, we've actually started the process. The Perseverance rover, NASA's Perseverance rover, is collecting samples of soil and rock. We've got more than 30 samples now have been collected by that rover. And the plan up until early this year had been that the rover is going to transfer those samples to a future mission in the later this decade that with the help of the European Space Agency would bring those samples back to the Earth. That's at risk now. The government is saying they don't want to do that mission now because it's very expensive and they have priorities in other places. Some parts of the government are saying not do it. Some other parts of the government are saying, yes, let's do it. So there's a fight going on now in the US government over the future of that program. But we are at least doing the first part of it, collecting some very well characterized samples and putting them in tubes like this. This is an example of a Perseverance rover sample tube, and the sample is about that much of it. And we'll have them there on Mars ready for that future mission to bring back whenever we can make it a priority and figure out how to pay for it.
And that's the problem.
That's right. Thank you, sir.
Sure.
I would like to, Dr. Bell, before we end, I'd like to ask a couple of quick questions in the chat. Is Martian soil stable enough to tunnel under?
It's basically the same as the Earth. If you dig deep enough, you run into rock instead of soil, right? And that's what you really want to tunnel into is the rock.
Okay. And are the effectiveness of solar panels reduced on Mars due to the distance from the sun?
Yes. And it changes a lot over the course of the Martian year. It's a 40% change in how intense the sunlight is between the wintertime and the summertime on Mars. And of course, it's 1.5 times farther away. So somebody do the math, 1.5 squared less power per unit area on a solar panel. So you need twice as much, more than twice as much area to get the same power as you would on the Earth.
Is geothermal energy a viable source for energy on Mars?
I don't know. As I said earlier, one of the things I'd like to do is really measure, it's called the heat flux. How much heat is coming out of Mars? We don't know.
Okay, and Karun, last question goes to you.
Sorry, ma'am, my hand was raised from the previous question.
Okay. Thank you, Dr. Bell, for the extra time you spent with our wonderful students. In respect for Dr. Bell's time, we are going to end the meeting here. This will be posted on YouTube and updated in the syllabus. Thank you so much. I appreciate all of you being here, your wonderful questions, and I will see everyone tomorrow. Check the syllabus for the time. Make sure you're here at the right time. Yes, sir.
Nicole, thank you all for the great questions. It's so exciting to hear your questions and to learn about the projects you're working on. And thank you, Nicole, for inviting me to participate in what looks like a great program.
It's incredible. We have 101 students this year all over the world, and we are so thankful.
Fantastic.
Thank you, everyone. I will see you tomorrow. If you haven't already submitted your outline, please do that as soon as possible. It's due in 6 hours. It shouldn't take you more than 5 minutes to fill it in and email it to me. Have a great day, everyone. Bye.
Bye. Thank you.
Bye.
Goodbye. Thank you.
Thank you.
Bye,
Bye.
Mrs. Thank you.
Bye.